Alright guys, we are going with part 4 of our unit on kinetics. Yesterday we stopped where we plug a second order reaction and then we change the y axis, the y. But today we need to do another example where we will be changing the x. So I need for you to enter your data on the time on L1 right now. Time on L1. Remember, it is start, edit. Before you do that, make sure you clear your list. Remember from yesterday, to clear your list, you do second plus, it is number 4, clear all list. Now do start, do edit, enter your time on L1 and enter your concentration on L2. And I need for you to go on top of L2, go to L3 and then take the natural log of L2, put it on L3. The natural log of L2, put it on L3. Take go to L4 and then do L2, the reciprocal button right here. L2, the reciprocal button. Now we have our L1, which has the time. We have L2 with the concentration. We have L3 with the natural log of the concentration. We have L4 with the reciprocal of the concentration. Now we are going to do the math. They ask if it's 0, first or second order. To answer that question, we need to calculate. Okay, so let's do Cal. Let's go to start. Okay, everybody go to start, go to calc, go to number 4, and then we are going to plug our L1 and L2, L1, L2, enter. We check our R, the linear correlation coefficient constant, it is 0.90. Do second, enter. Second, enter. Let's go back and replace L2 by L3. L2 by L3. And then press calculate again. It is 0.97. 0.97. Let's do second, enter. We will go back and replace L3 by L4, but put comma, do VOS, Y VOS, number 1 should be function, press enter. Enter. So we have our Y1. Let's do enter again. This is 0.999. So this is definitely a second order. It is a second order reaction. Now that we know for second order, the next question is, okay, I don't know why I have this here. The next question is calculate the rate constant. The rate constant. They asked for the rate constant. Remember yesterday we said the absolute value of the slope is your rate constant. The absolute value of your slope is the rate constant. Alright, next they ask to find half-life. Now that we know it is a second order reaction, we can use two different methods to find half-lives. I'm going to use the graphical method. The graphical method. That's what we will do. We are going. They ask for half-life. They are asking for what? Is that X or Y? They are asking for time. If they are asking for time, that means they are asking for X. If they are asking for X, we need Y. If they say half-life, this is the initial concentration. Initial concentration. We need, after the first half-life, it will be half of that initial concentration, which is 0.005. In other words, our concentration, we need to know when Y equal if it's second order, that means this is inverse. When Y equal the reciprocal of 0.005, we need to find X. Okay, so let's go under Y equal. Y equal, yes, Y equal, beside Y2 equal, let's go to Y2 equal. Go down, Y2 equal. Why don't we enter 0.005? But because this is second order, what we have in the graph is really the reciprocal of that. And then do reciprocal of 0.05. Okay, press enter. Let's graph it. Let's graph to see what happened. Do graph. And then do zoom 9. Let's see if we have, we don't see the intersection. When you don't see the intersection, that means that Y is outside the range that you need. You would do zoom 3 to zoom out. Zoom out. Let's see if we see the intersection. Yes. So you put all your points very, very close to each other if you are outside the range for you to see the points. Now we have a Y, we need an X. When you have a Y, you need an X. Go to start. No, we already did start call. Okay, you can clear that. And if I have to do second trace, which is called second trace. Remember when we had the X, we wanted the Y, we did the number 1 for the value to enter the X. Now that we have Y, we need X. I need for you to go to number 5 for intersection. Number 5. When you have a Y, you need an X. Go to second trace, number 5, which is intersection. And then press enter. Press enter again until you see the word intersection right here. Press enter again. This is intersection. That means when Y equal 200, when Y, is that Y? The natural log of your Y is the 200, then your X is that number. Okay, let me repeat. When they give you an X, they ask you for Y. You do second trace, number 1, which is value. You enter your X to find your Y. When they give you a Y, they ask you for X. You need to do the same thing. Second trace, but you do number 5 for intersection to find your X. If you have an error message, that means it is outside the range, you go back and do zoom 3 to zoom out to find until you find your intersection. So this is part of yesterday's lesson. Let's move on. I'm not doing this. You can do it for your practice. Now, this is a very good summary of everything we have done so far. So you can pause the video and take notes for that table. When the reaction is 0 order, the weight law, that's what you write, because it is concentration A to the 0. The weight law is just K. And then this is the integrated weight law. The half-life is initial concentration over 2K, and the slope is negative K. When it is first order, this is the weight law. This is the integrated weight law. This is the half-life and the slope. When it is second order, this is the way you write the differential weight law. This is the integrated weight law. This is the half-life and this is the slope. So this is a summary of everything we have done. This is here's the objective for today's lesson. Today we will be able to explain the difference between collisions that convert reactants to products and those that do not, in terms of energy distribution and molecular orientation. Your homework is the lab report. So I hope you have done all your quests. So the homework is the lab report. I have another quest. I leave it for next week because of the lab report. Now, this is just a review. We already discussed this. As you can see here, for a chemical reaction to take place, we need two things. We need the particles to collide. Okay? Not only they need to collide, they need to collide with enough energy. Alright? When you increase the temperature, you increase the average kinetic energy, and they have a better chance to react. Not only they need to react with enough energy, they also need to react with the right orientation. If they are colliding, they are not colliding with the right orientation, nothing will happen. Okay, let's close this and go back. And if I to review that activation energy, that energy diagram graph. Let me tell you different names you may see for your x-axis. You may see reaction coordinate. You may see reaction progress. You may see reaction pathway. They all need the same thing. They mean the same thing. Reaction coordinate, reaction progress, reaction pathway. They may even use time. So remember, here you will have your reactants. From here to here, this is your activation energy. And from here to here is your delta H. Or you may also see delta E. For the reverse reaction, listen carefully. You may see that on your next test. If from here to here is the activation energy for the forward reaction, for the reverse reaction, if we are going the other way, the reverse reaction, the activation energy will be from here to here. And the difference between the activation energy of the forward reaction and the activation energy for the reverse reaction is your delta E, your delta H. The difference between the two activation energy. And I need to remember, activation energy is always positive. You need to add heat for the reaction to take place. All right? And then here on top, we have what we call a transition state, an activated complex. So if we don't have enough energy, if we don't have the right orientation, that activated complex may go back to reactant and you don't form any product. Two conditions for a reaction to take place. You need enough energy, you need the right orientation. You know, when you use a catalyst, then you use a different pathway for the reaction. It will lower the activation energy. You know, a biological a catalyst is called an enzyme. We already discussed that graph, and for you to remember what we said, if we have, this is lower energy in black or blue, whatever color you see. Okay, lower energy. This is the minimum, the activation energy, the minimum amount of energy you need for the reaction to take place. At a higher energy, you have a curve that is more flat. Right here at that temperature, this is only, at lower temperature, this is the amount of particles that will have enough energy for the reaction to take place. But when you go to a higher temperature, not only you have those blue, you also have all of this. You have more particles that have enough energy for the reaction to take place. When you see E subscript A, it is activation energy. Alright. Now, this equation you need for your lab report, that's where I wanted to stop. You need this, and for you to listen carefully. This is called the Arrhenius Equation, but we are not going to use it. Let me put this larger, and I will come back to that calculator so I can see my little note right here. Okay, so this this is the equation, but we are not going to use it in this form. I'm going to change it to a linear equation. That's what you will need to graph to answer the questions from your post lab. Listen carefully. I'm going to take the natural log of both sides. Natural log of both sides. So I have the natural log of k, this is our rate constant, equal, if I take the natural log of this part, I really have negative activation energy over RT plus the natural log of A. That natural log, that A is a constant. It is called the Arrhenius constant. You don't have to worry about it. What I want you to see here, what I really want you to learn here is, this is in the form of a linear equation. The natural log of K equal negative activation energy over R, which is the gas constant. It is the energy gas constant. That means it has to be 8.31. This is the energy gas constant. This is inverse temperature. This is our temperature right here, plus the natural log of A, which you don't have to worry about. And if I to look at this carefully, you need it. This is your Y. This is the slope of the line, and this is your X. This is your X. So whenever you change, you do your experiment, you change the temperature. That's the only thing that will change the rate constant. Changing the temperature will change the rate constant. So what you need to plug is, you are going to plug the natural log of the rate constant versus the reciprocal of your temperature in Kelvin. When you do that, you should get a straight line, and the slope of the line is negative activation energy over R. An AP question will ask you to calculate the activation energy. So activation energy equal, because we said negative activation energy over R equal slope. So when you graph your data, activation energy equal, therefore activation energy equal negative slope time the energy R. This is what you need. Okay? Activation energy equal negative slope times the energy R, which is 8.314. Why don't we do an example before we run out of time? Okay, this is what I told you. This is your y-axis. It is the natural log of k. Remember, natural log of k is your y. Remember, the x-axis is the reciprocal of your Kelvin temperature. And remember, the slope of the line is negative activation energy over R. So let's get ready to plug some numbers and solve a problem right here. Okay, so why don't you pull out your calculator right now? They ask you, this is the last problem we will solve. They ask to calculate the activation energy. This is what we will do. Now, remember I said you should always read, okay, the title of your graph right here. Always read the title of each column. Everybody, why don't we clear our list? Okay, second, memory. Number what? 4, clear list. Okay, let's get our calculator. You see, as you can see today, we have a pink calculator for the girls. Yesterday we had a gray one for the boys. We have a pen calculator. Let's go and use our pen calculator. Enter. So we clear our list. You can clear? Clear? Let's go to start. Edit. Why don't we quickly enter our data? Remember time. Let's go to L1. To the left. L1. Okay, time. For now, let's just enter them the way they are. And we are going to do a batch conversion. The way they are. Let's go with 0.2 for it. This is the temperature in L1. Yes. Oh, I'm sorry. You are right. You are right. It is 20, 30. Don't worry. Don't worry. 20, 30, 40, 50, 60. Let's go to our L2. This is K. Let's do something quick to save time. Why don't we change all of those to the same exponent? Okay, let's change, because we have what? 2 -4. Why don't we change them to -4? -4, it will be what? 20 times 10, 20. Don't do anything for this yet. Don't worry about the exponent. Right? Okay, I need for you to type 20 for this one. Oh yeah, 20. I need for you to type 73 for this one. Say that again. Okay, you are right. You are right. It is point 2. Point 2. So I need for you to type point 2 here. Point 2. Type point 73. Leave this the way it is. Leave this the way it is. And this one is 29. Is that right? 29. Now, let's put our calculator up again. Okay, very good, very good. This is, okay, I thought you already had them. Okay, point 2. L2 point 2. 0.73. 2.7. 9.1. 29. Say that again. 0.73. 0.2. 0.73. 2.7. 9.1. 29. Is that right? Now, let's do, we have a lot of work here to do. Let's go on L1. We don't want degrees Celsius, is that right? We want Kelvin. So why don't we go all the way on L1? All the way. We are telling the calculator to take L1. So do second 1 plus 273. So we convert all our degrees Celsius to Kelvin. Enter. Okay, at once. Now let's go to L2. All the way up. We are telling the calculator to do second L2, second L2, second EE, second EE, second exponent, -4. We are telling the calculator to take everything in L2, make it times 10 to the -4. Is that right? Enter. -4, not -5. Okay. Oh, okay. All right. I thought I had what you had typed here. Now we are still not done. We want y to be what? The natural log of the concentration. So go all the way on top of L2 and then do natural log ln L2. L2, because we don't need the concentration, we need the natural log. Enter. So now what we have is, we have the reciprocal. Did we do reciprocal? No, we did not. Let's go back on top of L1. Because what we have here is Kelvin. But we need reciprocal of the Kelvin. We need a natural log of K. So go on top of L1 and then do L1 reciprocal. Yes, enter. Now we have them the way they should be. We have the reciprocal of L1 for as our x. We have the natural log of K as our y. Now we can calculate. Why don't we go to second? It's not true. It's not true. Let's go to start. Okay, start. Let's go to start. Calc. Number 4. Enter. Okay. So this is our R, which is 0.99, which is good. This is the slope of the line, which is -12174. This is the slope. and they ask to find activation energy. So all we have to do is activation energy equal, okay, E subscript A equal the negative slope that we have here that become positive, a positive number, negative the slope times R, which is 8.31. So you can all do that. Let's go back to the calculator. Okay, we find activation energy and what they ask for. Okay, who has the answer? What is the activation energy? They say you already did that? Okay, here's the slope. This is positive. Okay, alright, this is 101. Okay, activation energy equal 101,000 what? 165. Is that right? 165. What is the unit for activation energy? It is joule, because it is energy. It is joule. Alright, so when you have an energy diagram that has a very low, high activation energy, that means the reaction is slow. If it has a low activation energy, it is faster. Now, let me show you different maths. I'm not going to solve this problem. I'm going to stop right now. But I'm just telling you, they can change the temperature and they ask you to find the activation energy, the Y, the concentration, or they can change the concentration and ask you for the time. The same thing we did with the other part of the unit. So they can change X and ask you for Y. They can change Y and ask you for X. Alright, thank you very much for your patience. We are pretty much done. We have one more lesson in this unit. One more on reaction mechanisms and we will be done. And you know what it means? You need to be ready for your free responses and your tests. So make sure you take care of all your quests and make sure you have your lab report before we start the free responses. Okay, so I hope to see you next class. Bye-bye.